Hello.
But we picked up
Hi.
license for
We'll be starting shortly.
Sounds good. Morning.
No.
Good morning.
Morning.
How you doing, Anas?
Good. How are you?
Good. Good morning, everyone. John, so it's 11 now, so we can start.
John, I think you're muted. John, we can't hear you.
John, you're on mute.
Okay, I got it, Nana. Okay, I realized I was muted, so now I'm unmuted, so you didn't hear whatever I said. I was just saying, good day, everyone, and welcome back to Varsity 2021. If today is your first time joining us, again, we had a blast last week, and we are going to do so this week as well. A few housekeeping. You find the recordings in Slack. All the course material, data set, Python code, you will find that in Varsity at GitHub. If you are finding any difficulty doing so, just send a note in chat, or you can do so in Slack as well. Today's topic is on data exploration and visualization. And our esteemed instructor for Module 2, that is today's or this week's topic, is Mr. Anas Bedwari. Anas has a master's in computer science and another master's in engineering. He is the lead data scientist and research faculty at the Innovation Center for Biomedical Informatics at Georgetown University in Washington, D.C. He teaches data science courses in the Georgetown Master's Program in Health, Informatics, and Data Science. In addition to teaching, he also leads research efforts in health data science, clinical informatics, and health IT. He has many years' experience as a health data scientist with an extensive background in software and data engineering. He has demonstrated a history of leading and implementing data science and machine learning projects in healthcare. So in addition to all this, he has designed and built clinical research data warehouses and developed predictive models for disease risk outcomes, leveraging big data analytics and data integration from various sources, including genomics data and imaging data. So we are pleased and have the pleasure to have Mr. Anas with us today. So let's welcome Anas by waving your hands. Okay, Anas, you have the audience. It's all yours.
All right. Thank you, John. I appreciate the kind introduction. Yeah, I don't think I need to introduce myself after that, but
I
yeah.
don't think we can hear you. I don't know if it's only me, but somehow we can hear you, or I can.
Can you,
Oh, I can hear him clearly.
Yeah, he's fine.
Yes, we can
I
hear.
can hear you.
okay, I guess it's on your end, John.
Okay, I can hear you now. Yeah, you are,
Okay,
you are fine. You are
good.
good.
Good, good. Okay, so as John said, so my name is Anas Bilwal. You can call me Anas, and my background is health data science and also data engineering, systems medicine, biomedical informatics. So name it, I was always placed in all the phases of any healthcare or health informatics project. So I've worked on different phases. So I kind of like get the full picture, but I'm not an expert in any of them. Today's topic, what I want us to do, and do you guys see my screen or not yet?
Not yet. You have to share it.
Not yet. Okay.
Yeah.
Okay. How about now?
Yes, we see it.
All right. Great. So the module 2, we're gonna focus on data exploration and visualization, and the idea is to and this will be done in a context of clinical informatics, so which is slightly different from regular data science project life cycles. So at the end of 2 days of workshops, I want us to get the basics of data manipulation and visualization. So we're not going to dive deep into the theory of imputation or visualization, but more like getting the code snippets and getting the tools to allow you to do some of the work that you will need later in other modules to build those machine learning models. So today is about the basics. So, and if you're a novice, that's great, and we're gonna move very slow. So don't be afraid of asking questions or stopping me. So just unmute and ask me questions. But also, if you're an expert, don't. This would be a good review of these modules and these steps. So, as I said, we're going to talk about data exploration in the context of clinical data and observational research. And we're going to touch a little bit on some challenges of clinical data mining workflows. And then after that, we're going to shift gears and talk a little bit about basics of data exploration and visualization. And one last thing that we're going to do before we move on to the hands-ons is mapping data types to visualization. So a good understanding of the data that is underlying your visual or is very important to make actually good visuals. Okay, I see that someone wants to annotate. Okay.
Oh no, you can cancel that. I did it by mistake.
Okay, all right. So how do we cancel this? Stop sharing, annotate. Okay, all right, we're good. All right, so exploration and visualization really sits at the core of a life cycle, the data science project life cycle. And if you see it here, kind of all these steps land themselves in an iterative process. So you are really not always doing this in a sequential way, but always coming back to each step and evaluating and redesigning your research question, redesigning your data, reintegrating your data. And really, I mean, if you ask any data scientist, like 90% of the time is actually data integration and putting that data together for the analysis. So, and that's the less fun part of it. And the fun part of it, which is building models and tuning them, that's probably 10% of the time or less. So having the basics of understanding where your data is coming from, is my data complete? Can I put it in a certain format to understand it and have some insights, is very important. And once you move on to the analysis, you might go back also to the visualization because, for example, I built a model and I need to evaluate the metric like AUROC. So I'm building a curve that can tell me how good my model is. I can also plot the predictors and how strong the predictors are. And then I can also plot my insights, evaluating my models, evaluating my outputs, confusion matrix, for example. So really, the exploration is not one step, and we see it often. If you look at like all the Kaggle challenges, for example, you'll find EDA, and that's it. Like you do exploration, and you do it one time, and then you move on. That's not what really happens in your data science project lifecycle. Any questions? Is that clear or? Good. Okay. Good. All right. So moving on, the clinical data mining workflow is slightly different. So, and by clinical data, I mean observational data, data that was generated in a primary care setting during an encounter or interaction between a patient and the healthcare provider. And that data is sitting in a database. So it becomes some retrospective data that you can analyze for, and we call it secondary use of data. So we look at data that's historical data to analyze it, to build models, to answer questions. And this process often starts by posing the right research question, identifying where your data is, because data in healthcare is fragmented. It might be in different databases. So you want the full picture of a patient, right? And then you're doing some extract and transforming the data, what we call ETLs, extract, transform, and load. And after that, you have one data frame that is ready for analysis. But again, it's an iterative process. So it's kind of similar to the data science lifecycle that we saw before, but it's slightly different. And the questions that we can ask from historical data or observational data are usually descriptive, explorative, inferential, and predictive. One thing that's clinical data or observational data is not really good at are causal questions or deterministic questions, where you're trying to understand the mechanism on why, for example, a certain, for example, drug affects the human body, or like what would be the pathway. But you're more likely to say questions like, can I predict an outcome of a patient if they take a certain drug?
Anas, I have a question.
Yes. Yeah.
Yeah, so you're talking about extracting data from an electronic health record system, for example,
Correct.
of which there are thousands, right? And so this is the conundrum about it. Are there any extraction programs that kind of work across big EHR systems for that process?
That's an amazing question. So and we're gonna touch on this, and we're gonna like talk about common data models. And
Okay.
so people, what they're doing, they're trying to bring data into a format from all these EHR systems to one clinical data warehouse, where you can build analytics on top of that that could actually be used across systems. So if say, for example, Howard Medical Center, they have their own clinical data warehouse and it's standardized, then we can use the same queries or the same programs to analyze it.
Okay.
And actually, like we have one project with, I think, Georgetown, and through GUCTS, through CTSA, we have a webcam, which is the same, it's a clinical research unit program, or EHR, if you will. And we collect data in Howard and we collect data in Georgetown, and it's in the same format. And then we build dashboards and explore it on top of that. So we can see both data sets since they're using the same systems.
Okay. And so you'll share more or a link about that process of extracting?
Yeah. Yeah.
Okay. Thank you. Thank you.
Yeah. Yeah. Okay. So let's take an example of a patient that comes into a hospital. They have a poorly controlled diabetes, for example. And so they're on a first-line treatment, and the physician at this point needs to make a decision. What would be the second line treatment or medication that they can give the patient. Often there are guidelines, right? So there are few medications that they can give, but eventually the clinician makes the decision based on their expertise, based on some patterns that they've seen. So what if, as a data scientist, you have access to thousands or millions of data points about demographics of patients, diagnosis, labs, procedures, claims, and also the notes? So at that point, can we maybe provide a consult, we call it an informatics consult, where we can say, here's what we think would happen if you give patient drug A versus giving patient drug B. And to do this, like say you have a database, to do this, you'll want to actually find the patients that look like John Doe, right? So give me all patients with the similar phenotype, we call it a phenotype. And then after that, what you would do, you'd want to identify the type of exposure. So which group took drug A, which group took drug B, which group took drug C, and then see what would be the outcome. And then if you provide it as an information, basically as a report, then the clinician, you're helping the clinician make that decision given some historical data. So if you're familiar, like if you come from a healthcare background, you might think about precision medicine or personalized medicine, right? So why is this difficult? And I want to ask the people with a little bit of background in healthcare, why would this be difficult or even technical? Like, why is this, we're not there? Why the promise of personalized medicine is not achievable? It seems very easy, right? Like we can look at some data, filter it, and we look at certain outcomes, but we're still not there. Any idea?
It's still cost prohibitive, and we don't yet have efficient ways to test for the phenotype for the patient to receive that particular, some unique function. We've not yet created that for big systems. Oh no, we lost our instructor.
Trying to come back. I'm not sure how it's. Hello? Do you guys hear me? Hello?
We do hear
Yeah,
you.
we can hear you, but we can't see you.
Oh, wow. Not sure what happened.
Low bandwidth.
Apologize. Yeah, it does say load in. Let me try to share my content.
We can still see the slides.
Oh, you can?
Yeah, we just can't see your thumbnail.
I'll stop my video again, share it again. Do you see me now?
No, not yet.
No.
How about now?
Not you, but your slides.
Hmm.
Oh no, we can see you. You have a
I see
separate.
you now. Yep.
Yeah.
All right, perfect. Technical difficulties. Okay, great, Jay. Perfect. Okay, so I guess like you were answering the question and it's kind of cut off. So you said cost prohibitive, right?
Yeah, because we don't yet have that sort of technology to apply on such a level, like in a big healthcare system, and to identify specifically the patient that would, match, that specialized treatment.
That's a very good point. Yeah. I think cost is one. We can also think about. I mean, you would also think that big hospitals would have the money actually to do something like this. Now, from a technical standpoint, I think there is an issue of availability of the data. So data in healthcare is very challenging. And I will draw like this example, for example, with say you go on Amazon, for example, and you make a purchase, and they can easily predict what you're going to buy next, right? And they can send you this ad, and we all say, "Oh, I was thinking of something, and the ad appeared on Facebook." So that's something that happens, and they're very good at it, right? But we're still not able to do something similar in healthcare, and for many reasons, and some of them are technical, some of them are costs, right? So let's think about three concepts here in this slide. So we have the phenotype, right? And we have the exposure. What medication? Exposure can be medication, can be a medical procedure, can be your genetic risk. For example, if you have a mutation, it can be a surgery. And then the outcome can be, okay, is my disease controlled? Did I survive 5 years in life? Like if I had cancer, did I develop a toxicity or not? So these are certain types of what we call outcomes. So they're not really an easy outcome. Now, if we go back to the analogy with like advertisement, the concepts of outcome is very easy. It's either I bought something or I didn't buy something. I clicked on something, I didn't click on something. The phenotype is easy, and it is a closed system, right? Because you go in, you are tracked, and then we have all the information about the person and their habits, on the site and what they're gonna do next. So, however, we don't really have that in healthcare. And the reason is this: the way we designed EHR systems, we designed them for billing, and so the concepts of outcome or phenotype or exposure are not readily available in these databases, right? So if I want to know, for example, if the patient progressed or not, or the disease progressed, I'll have to go into the chart and read the clinical note to actually identify that and say, okay, this patient progressed, and then I'm going to use that outcome in my analysis. So many challenges in data in healthcare, and it is often that's like we have an avalanche of data, and we are the question we're asking: how am I supposed to analyze this? So data in healthcare is messy. And that's an understatement. It's incomplete because you don't have the full picture of a patient. A patient can go to multiple providers. It's fragmented even within the healthcare system. Even within a hospital, you have some data in the pharmacy database, you have some data in the oncology EHR, you have some data in the outpatient EHR. So it is fragmented in itself. Ever-changing data. So anyone can think why healthcare data is ever changing.
Because we always change it. Like we're in a process from year to year of relabeling variables, adding variables, merging templates. Yeah, we're in a constant process. So
absolutely,
yeah.
And I think what we call it also, we can call this concept as a medical or shelf life of medical data. So medical data can actually expire, and what I mean by that, practice changes from year to year. So new drugs get introduced, procedures change. So it's not always the same. And there was a research paper recently that actually looked at the predictability or the power of data from 6 months previous, 6 months of prior to the last visit of a patient, and 4 years worth of data prior to that. And they tested few prediction models like readmission, I think mortality, and they found that's only like the 6 months of data that is closest to the date of prediction is most predictive. And the data, 4 years of worth of data before that, was not as good. So it is very, very good to like understand this, because sometimes we embark on these journeys of building registries, and it takes a year, 2, 3 years, and then the data by then is probably too old to glean any information from it. Another issue with the healthcare data, the healthcare data is very biased, and one, it has our own biases and disparities that can be included into that. And there are also other types of biases that are more technical, like missing data bias. For example, a patient seeks or does not seek healthcare. So they get sick and they don't come to the hospital, or they developed an adverse event and they didn't report it. So that's missing data within patient timeline that we're not aware of, okay? There's misclassification bias. So whether the patient had a disease or not, even within the care, sometimes we might make an error in classifying the patient. We might also not record patients that are healthy, so we only record patients that are sick. So that's also one type of misclassification bias. And I think yeah, so I think also there is self-selection bias, right? So I think that was the very first one where I talked about missing data, but that was actually self-selection bias. And missing data is when you're doing your own research, you might also, when you do your imputation, you might include some of that bias. The last one is privacy. So healthcare data is not like any other type of data, because you have to make sure you follow the regulation, you apply to your IRBs, it's HIPAA protected. So when you're analyzing the data, you need to be very careful in like HIPAA compliant servers. So those are like some technical also challenges and privacy challenges that we need to be careful and make sure that we are respecting the privacy of the patients. Okay, so this is an example of exposure misclassification, and the idea here, what this top plot shows, is that the drug exposure, the true drug exposure event might be different from what is recorded, for example, in a pharmacy claim database, and so say patient comes to a hospital, they get prescribed a free sample, so it's 15 days of free sample. Then they go on to the pharmacy, fill the sample for 30 days. They miss few doses in between. And then they take the medication for say 7 days, and then they stop. So this is what actually happened. If we go and extract data from pharmacy database, or from the claims, we receive some data from the claims and try to analyze it, we're going to see that the patient took the medication for 30 days, then there is a gap, then took the medication for 30 days. And this is very challenging, and there are things that we can do about this. For example, if we go back to the EHR and we have the notes, we might actually find out that the patient received some free prescription. However, there are things that we can't do, like missed doses. That's something that's about medication adherence, or like the patient discontinued use. Those are some things that we can't really account for unless we track the patient, unless we have some systems for feedback from the patient. And often what you end up doing if you have data like this is to create these rules of whether, if I have 2 exposures or to the medication, then maybe between here and here, the patient actually had the medication as well. And I can go and look at other systems and see if the patient actually took the medication in other spots. So it's all about bringing data from multiple sources to get a full picture of the patient. So And that's what you would hear often. It's called integration. It's called bringing data into clinical data warehouses, bringing data into data lakes. It's kind of like the same words. Well, what it means is that let's look at all these systems and bring the data, build some ETL, some integration layer that can allow us to integrate the data into formats that we can go and do these one-off like research projects. And the reason this would allow us to actually have a full picture of the patient. And going back to systems that can actually go across the other EHR systems or other institutions, we have what we call common data models. And I2B2 is one example of that, which means that can we build a tool that sits on top of a common data schema or a common database, and that can help us analyze the data in a uniform way across multiple institutions. Any questions so far? Okay. So is the screen big enough? Do you guys see the slides well?
Yes, it's good now.
It's good? It's good now?
Yes,
Okay.
it's good enough.
All right. Okay, moving on. So we talked about common data models, right? So it's a common data model is just a schema. So if you're familiar with databases, it's a common schema, and we bring our data into that schema to analyze it and apply some systematic analysis using some standard libraries. So there are multiple, we call them distributed health data networks, and the one I mentioned was I2B2. There is Odyssey, or it's also called Observational Health Data Science Informatics Network. There's TriNetX, PCoriNet, and for adverse events, you have the FDA database. And I guess the takeaway, like you don't really need to understand this deeply, but the reason I mentioned this is that the common data models might have some terminologies that are specific to those common data models, right? So if I'm trying to analyze some healthcare data and I receive some data and I have some terminology, I want to understand what is the coding, right? I want to understand, are they using OMAP to code the diagnosis? Are they using for example, SNOMED codes? Are they using ICD codes? So understanding where your data came from is key to being able to analyze it. Okay. Data in healthcare in general is very heterogeneous. So you can find data in a structured format, which are the tables. They're consistent, organized, tabular format. You have the terminologies for each concept or type, diagnosis, ICD codes. You have NDC codes for medication, and you can often query these using SQL. The other type, which is more challenging, is unstructured data, and it has a wealth of information that makes your patient record or patient timeline more complete. So it is often that when you're looking at a health data science project, you might want to also get information from your clinical notes. So the clinical text is, some people call it natural language processing, but it is very different from natural language. There is a lot of abbreviations and acronyms. Doctors also use a lot of copy pasting. They use headers, and so it's very different from just a natural text. And that's why if you're familiar with word embeddings, which are these language models that can help us analyze natural language, they're not easily applicable to clinical text. And what people do, they develop specific language models, like for example, bio Word2Vec or clinical texts Word2Vec, which means can we develop natural language models that are specific for clinical text that could help us either do some detection in those, some automatic detection in the clinical notes. The second type of data is imaging. So we're talking about MRIs, X-rays, CT scans, and this has a wealth of information as well, because you might want to, for example, build a model that can detect a tumor. You might want to build a model that can segment the tumor in an MRI. So those are all use cases that's machine learning or deep learning can be applied to imaging data. And you have signals, and signals are usually not very common in healthcare unless like you have someone in the ICU and you're tracking their EKG, for example. So at that time you have a continuous sensor, continuous data, and you can maybe build a model that uses time series data to maybe predict whether the patient is going to have a heart attack, or whether the patient is in distress, or whether the patient might develop sepsis, for example. So it's key to understand that the data in healthcare is not homogeneous. It's existing in different formats, and even within your exploration or your process of trying to create that data frame that is ready for analysis, you might have to touch on multiple of these data types. And as I said, information in an EHR system has this inherent timeline. Okay, so patient A comes to the hospital, they see a nurse, they get their weight and BMI taken, and then, or height taken, and then they see the physician, there is a physician note, and all of these events happen across a timeline. And this is very important. If you want to analyze healthcare data, you want to understand that the information has an inherent time ordering for all the generated events. Is this clear? Okay, I see someone writing about HL7. So HL7 is a protocol that can allow you to send data from one EHR system to another. So it's more of an exchange, and another similar protocol is FHIR. And these are protocols that allow two systems to communicate. And it can be useful mostly in terms of like exchanging data. For example, I went to hospital A, and hospital A wants to send data to hospital B, then I can use an HL7. Or even within the same systems or same hospital, the different databases might use HL7 to communicate. Yeah, correct. Yeah, so it is a granular event. So correct. I'm looking at the chat. So what was said is that there is a granular event here. All the events are one event, and we're plotting it across a timeline for a patient for each specific encounter. Okay, so how do we analyze this, right? So we have a timeline, and we usually need data in a tabular format to analyze it. And think about this, like you can do it in the most basic way. You can do it coding the data, reviewing the data manually, and then you code your patient matrix. And what we do with the patient matrix, and this is very important, we understand when the event happened, because, for example, I want to know if the exposure of interest happened before the outcome, right? And then I often have a baseline or an index date that I'm using to do some prediction in the future. So what we do, we bin the data, for example, 6 months, the past 6 months, the past year, the past 5 years. And we see if the events happened within those windows of time. For example, did the patient have a life-threatening event? And you can think about it, right? If a patient had like a life-threatening event in 2011, it's not very as important as a patient having a life event closer to the last visit. Because if I'm doing prediction of mortality, I want to give this more weight, right? Like bins here that are closer to the index date might need more weight, right? But the way going back, I just want to explain this. So what we do, we look at the different diagnoses that happened, and we just assign them bins, assign them values. So you can assign them a 0 or 1. Either it happened or it didn't happen. Or you can also assign them some count of events. So did it happen twice, 3 times? And then you can maybe have some clinician expertise that could tell you, okay, weigh this more, for example, based on the task. For example, if we're predicting readmissions, maybe the weight of an event that's life-threatening is more than a weight of an event that's just a simple, for example, cold in that the patient developed. So those are few things that we think about when we're building this patient matrix. And this applies to all other types of data. So you're doing it for procedures, you're doing it for labs, you're doing it for visits, you're doing it for drugs. And you can also assign weights for drugs. For example, a chemo drug has more weight in predicting, for example, outcomes than ibuprofen, for example. So this is the most important, I think step, and we're going to build we're going to use pandas and some patient synthetic data to build a matrix like this. So this is really an important step, and I wanted to I wanted to drive it home. So please ask questions if you have them. Okay, we have a question. Should this not be defined by the ranking of the diagnosis? I'm not sure what you mean by the ranking of the diagnosis. So it is often that you can look at CMS, for example, has this categorization of different diagnoses, and it can give them different weights based on okay, billing. Yeah, possibly. Yeah, I mean, if you have access to billing data, you can do that ranking. But eventually, you might also. Yeah. So it's at the end. At the end, we are binning the data, and we are trying to bin it based on some criteria and give it different weights. That's the idea. Whether you do it, whether you have some other information that you can bring to the table, whether you have a clinician that actually give you the weights, it's all information that you can augment your timeline with. Okay, by binning the data, you mean binary values, some quantifiable or numeric data. Exactly. So the way we're binning is just an event. Did the event happen, 1 or 0, or the count of events? And this is very, very key, because when you're building a model, you often want those dummy variables, or like we call them dummy variables, which is like false or true. Did the patients have cancer? Did the patients have diabetes? So it's just a 1 or 0, right? And you might assign different weights by multiplying that one or that event by some specific weight. Okay, are we speaking about primary diagnosis or secondary diagnosis? I'm speaking about all types of diagnosis. So we don't really, once you look at the diagnosis table, you want to understand any type of diagnosis. You might want to organize it by primary diagnosis, but ideally what you do, you just try to construct a matrix with all the events possible for a patient. Okay, so let's move on. All right, so now that we kind of talked about healthcare data and got some understanding, we can go back to data exploration and visualization. And it is key to understand that there are two types of visualization. The first one is the one of today's topic, which is data exploration visualization, which is we still don't know what's true. So we are still trying to explore the data. We are still trying to glean some insight from that data. So that's the first step, right? And then there is the data presentation visualization, where we're storytelling with the data. So basically, you know what's true, you found some trends, and you built a dashboard, a nice dashboard, and you're presenting it to stakeholders to present some information or present some KPIs or that you're tracking, or some information that you're tracking. So we will be focusing on number one, because it's the one that is used in the data science lifecycle. Data exploration as a concept is much broader than visualization. So you can think about visualization as a sub module of that. And when we're doing data exploration, we can calculate characteristics of the data, summarize the data, do some descriptive statistics. You might also do some imputations, some scaling for your machine learning model. So it's good to understand that there is a slight difference. And the key motivations between doing this is to actually select the right tool for analysis. So when I look at my data, do I have enough data to do deep learning? Do I treat it as a classification or as a regression? Do I have the right values? How is my data coded? So all these are really good questions to answer when you're doing your data exploration and visualization. And one thing is also good about data visualization is that it uses the human ability to pick the patterns. For example, let's think about number of visits per day in a hospital. If you see it in a tabular format, it will be very difficult for you to actually see peaks of when, for example, over the weekend or over the holidays, we have a peak of an event or peak of infections, for example, of certain events. So we visualize the data in that format to actually see if there is maybe some seasonality in the data that we can see just by looking. Analysis, which was created by John Tukey, the famous statistician, is slightly different, but I guess now the difference is kind of blurred. The EDA is focused mainly on anomaly detection and clustering, but now like people use the two terms interchangeably. Okay, so this is a fun. I don't know if you've came across this funny presentation, and this is why you always need to visualize your data. And if you look here, you can see that the mean of your X, the mean of Y, and their standard deviations and the correlation doesn't change. But the actual points, even though we change them, and this is kind of silly, this TRX, but the idea is that you can change your data and visually, but you can still have some statistics that never change. So that's why it's really important to visualize your data. All right. Okay. Yeah, so the idea is that your statistics or basic statistics like mean, standard deviation, correlations might tell you something, but not always. So you want to visualize the data. Okay, this is another use case where you want to visualize the data, but it's slightly different. It's, say, for example, you have some chest x-rays from 2 hospitals, and the task as a data scientist is to predict pneumonia. So I have an chest x-ray, and it's a classification task, right? And you can build some deep learning model using CNN to predict the pneumonia versus non-pneumonia. Anyone can guess what happened. Like we can build the perfect model, but it could still not be, or a good model, it could still not be doing what it should be, which is detecting pneumonia. Okay, I'm looking at the chat, or anyone? Okay, let's look at the prevalence. So you have hospital A, which has 1% prevalence of pneumonia, and hospital B has 38% prevalence of pneumonia. Okay, I'll explain this. So there is something called hospital bias, and machine learning models are very good at that, like at detecting that and using it to make predictions. And what you want is to, when you build your model, to make sure that your models are not picking up some patterns that are due to the data, due to, or like existing in the data because they came from one hospital versus the other. And what the model did here was to detect this tiny annotation. So we have two, obviously in 2 systems or 2 hospitals, you might have 2 different machines that do x-rays, and then you have some different annotation or some hospital annotation. So the model, instead of learning the pneumonia where it was just learning whether the image was coming from hospital A or hospital B. And of course, since the prevalence is different here, it was assigning everyone coming from hospital A as not having pneumonia, and everyone coming from hospital B as having pneumonia. So you could actually get a model that's like, if you have a balanced data set, you could get a model that's close to over 80% accuracy just by trying to identify which chest x-ray belongs to which hospital. And this is one it's not a very kind of like easy thing to think about, but it is very important to visualize and try to find these patterns that might bias your models and the output of your models. Okay, always visualize your results. And this is one project I worked on where we tried to use patient biomarkers, gene expression data, and some demographics to predict lung cancer. And at the end of the modeling, I often go back and visualize the predictors and their impact on the model. How are they impacting, or like you can think about it as are they pushing the risk towards having lung cancer, or are they pushing the risk of the general risk for the patient of not having lung cancer? So blue, you can think about it as protective, higher values of blue is protective, and higher values of red is actually not protective. And the issue here, you can see that smoking came up as protective, right? So why do I visualize this? It's to tell me that if my model, even though it was doing well, did it have some bias? Did it have, or is it using some feature in a way that it should not be using, right? So because it doesn't really make sense that smoking is a protective predictor for non-lung cancer, right? So you might always want to do this, like visualize your models, interpret your models. It's not about building a model and getting great accuracy, but it's actually understanding what your features are doing and do they make sense medically, right? Okay. So to be able to visualize data, we need to understand what are the data types. And I'm talking here about concepts like not integers and floats and strings that you encounter maybe like for computer science you encounter in programming, but more of a conceptual data type. So data types are in general categorical or numerical. And for categorical, we have nominal, which is basically gender, for example, female, male. And you can only do few operations on this, right? You can only do, like, is this different? Is this person female or not female, right? So, or does the person have diabetes or not diabetes? So they're all categorical variables. And it's the easiest, I guess, one of the easy ones to understand. Ordinal is a different type where you have ranking. And this is very common in survey data, for example. You have some patient health questionnaires and you have some scale. So there is a ranking between the values, but the values don't really, for example, the pain scale of 4 is not necessarily twice pain scale of 2. So there is an ordering, but the values are not quantitative, and that's why we often use this as a categorical variable. And there's a big debate about this, whether to use it as continuous and how many levels. If I have like 10 levels or 7 levels, then I use it as a continuous variable. Next, we have interval, which is an example of that would be a temperature in Fahrenheit, where the 0 doesn't really mean a true measurement. It's not really a 0. So you can't really, for example, temperature of 20 Fahrenheit is not really twice the temperature of 10. Like physically, it's kind of different. Ratio is the real number, or the where you can actually apply all kind of operations, and the 0 actually exists. So there is a true 0 in your data. So the weight of 0 is actually 0, and the weight of 10 pounds is actually twice 5 pounds. So really, I mean, I think that this is important to kind of know, but really the most important thing is to understand what is a categorical variable, what is a numerical variable, and what are some operations that are allowable on each type of data, because this is key to understanding which visual to map to that data. Okay, so as I said, it is important to map your visuals to the underlying data, and it is often that if you are coming to visualization from a data presentation or data presentation, you'll think about what I'm trying to convey. But usually, if you're coming from an exploration process or phase, you have some data and you have it in a specific format, and you start thinking, okay, how can I plot that data? So that's the key difference. So it's the underlying dimensionality of the data and the type of the data that define what plot are you going to use. And we're going to kind of explore it by dimensionality and by data types. Okay, so say, for example, I have types of visits in a patient or in an admission table, for example. That's a categorical variable, right? So it's in that case, I have one dimension, and it's just number of type. It's just types, and what I want at this point is a bar plot. So I'm calculating the frequency of visits or of outpatient visits, and I'm calculating the frequency of this category: emergency, urgent care, inpatient. You can also do pie charts. I don't like pie charts because they, as humans, it's really difficult to kind of like get the ratios from pie charts. So if you have two variables, I've done it. I use pie charts to do female, male, because it's like just two variables and you can see the difference between the two groups. But once you have a lot of variables, it's very difficult to actually understand it. So what you might want to do is bar plot and just have your percentage numbers here annotated with your percentage. Okay, we have a few questions. So where will you put time to event? Time, well, it really depends. You would treat time as continuous variable. Sometimes if you have year, like if you bin it by year, that becomes sometimes ordinal, but often it's a continuous variable. Aren't pie charts used if data don't have specific order? That is correct. So you can use a bar plot or a pie chart when your data is categorical. And what did we say? We said that if your data is nominal, there is no order in your data. You can use ordinal, like you can use it. I mean, there is a ranking. It would convey the percentage of that value of those ranking, like pain scale. But yeah, you would lose the ranking that you have. Okay, for numerical data and one dimension, so I have one column, say maybe age, I would plot a histogram. And what histograms do, they take your data, which is a continuous variable, and they bin it. They create all these bin, or they discretize that data and create bins and kind of show you the distribution of your data. So variables, like all numerical variables, histograms are great for plotting your distribution. And this is Gaussian, but normal distribution, but you might often have like different types of distributions. Okay, say we have two variables that are numerical, or two real numbers, age and BMI. In that case, we often use a scatter plot, right? So we're plotting here, for example, each patient, their age and their BMI. And these are often useful to kind of detect outliers on each side here. Okay. Now let's take a scatter plot is kind of similar here. Scatter plots and a density plot are kind of similar, but what we do here, it's kind of a heat map or 2D histogram. So you can think about it as like this 3D plot, but it's kind of flat on a 2 dimension, and you're trying to see here how many people are concentrated in each section here. So this, if we go back here, I don't really know how many patients, right? Like there might be multiple patients that have an age of say 47 and the BMI of 20. There might be multiple, but if I do this, I get a sense of that density. Okay, so another 2D plot is a line plot. And going back to the question of how do you treat time data, we often use it, we treat it as a real variable because there's an inherent sequential event. So your X usually has one value. So for example, at this point, we had one, for example, number of visits or some other event. And this is the, I think, cosine or sine of X. So you're plotting a real variable X, and you're plotting the Y variable here is the sine of X. So that's how you can show a line plot. Okay, one really good plot, and I use it a lot actually to show because usually you're looking at classes, especially for machine learning, especially for classification. You're looking at a categorical variable and a numerical variable, and you're trying to say, okay, what's the level, for example, of this variable in my two classes or in my two groups? And here what I'm plotting, and the outcome is either patient has diabetes or not. So I'm plotting my population, my population, and I have glucose level on the y-axis. And what this tells you, it tells you that the median of the diabetic patients, the median of glucose is higher than non-diabetic patients, right? And you can also identify outliers. So these are like really good plots for identifying your outliers. So if your data is outside these quantile ranges, you end up with outliers, and you might want to actually deal with those outliers. Another way of plotting one categorical variable against one numerical variable is violin plot, and you can think about this as like.
Would you like to
I think someone is unmuted. Okay, so what you want to think about here is this is a histogram that is sideways. All right, so it just gives you a little bit more information than this because it tells you where your data is concentrated for this group and how it's kind of like distributed. Okay. Okay, say we have two categorical variables. I have age groups and BMI category. So you might want to look at co-occurrence, like how many times, for example, the two variables co-occur. And here I'm plotting 4 age groups and 4 BMI groups: healthy, obese, overweight, and healthy. And this can tell me a little bit about the population I'm working with, right? So most of my population and most of the patients, this is the frequency of co-occurrence, which ends up being just the number of patients, right? So most of my population is between 18 and 44 and obese. So it's kind of just like an easy way of getting one kind of inference or one information about your data. And here you can see that, for example, I don't have anyone below the age of 18. I don't have anyone that is above the age of 45 and healthy low BMI. Okay, so what we can also do is plot, for example, number of visits or number of per year per month. And this is kind of like a heat map that tells you the number of visits per year per month, for example. So that's one way of treating the year and the month as categorical, and you're just trying to see what value of visits are in those heat maps or in those squares. Okay, so once you start having more data points, a lot of people start plotting the 3D plots. I don't really like those because you need an interactive interface, because usually what we do, we plot a 3D plot and put it on a 2D paper or say a PowerPoint. You lose that interactivity and you lose that ability to actually see in a 3D plot. So yeah, unless like you're doing a PCA with colors and you have a really like nice separation, I would say avoid 3D plots. For 3D data, there are like other alternatives. You can, for example, if I have 3 variables that are all real or all continuous, I can plot multiple scatter plots, and you can see here. So it's here it's a scatter plot of BMI against glucose, right? Age and glucose. And here it's just the histogram of that specific variable. So it's the histogram of glucose, the histogram of age, the histogram of BMI. This is useful for exploration, but it's not good for data presentation. So you can't just like plot this and tell someone, okay, you go figure it out, because you need to actually use this to understand your data and explore it. So what we usually do, I guess, here, we add one other dimension, and usually it's categorical, right? So say my outcome here is diabetes or no diabetes. I can color code the points or the patients. So you can see here, once we add that, we added some additional information, right? So we can see here that the diabetic patients, for example, cluster here in upper left. You might say, okay, there might be some trend, there might be some linear trend or relationship between BMI and glucose. The higher BMI, the higher your glucose, or like that. So that's what you can glean by adding like additional information or additional categorical information to your scatter plots. All right, so I think we're almost done with the slides. So I want to introduce the Python libraries we will be working with. There are few popular ones, and the main one that's most famous is Matplotlib, and it's a low-level library that provides it's kind of like provides you with the ability to customize your graphs, but it's a lot of coding. But we're still going to go through it and try to understand it, because a lot of other visualization tools use Matplotlib as the backend. So it's good to understand it. There's Pandas Visualization, which integrates very well with Pandas. And Seaborn can provide nicer, prettier graphs. And if you're coming from R, you might want to stick to ggplot. Honestly, I often use just Pandas Visualization or Seaborn. And if you want interactive plots, you can look into Plotly. And we're gonna do some of this, and some of Seaborn, and 1 or 2 graphs using Plotly. Sorry. So it's saying, can you, we have a question for Malik. He says, can you explain the diagonal graphs in the 3D visualization section? Okay. So going back to that, the diagonal here is the histogram, and it's the histogram of your BMI, for example, right? Because BMI and BMI, it's just the same variable, and this is the histogram of that event, of that continuous variable. Same thing here for glucose, then you have the histogram of glucose, which is the frequency of across multiple bins. Okay, for data manipulation, the focus will be pandas, and there are multiple other libraries that you can use for manipulation, but the main one in Python is pandas and NumPy. So pandas and NumPy go hand in hand. So if you're trying to build a machine learning model, you're likely to use one of these and to manipulate your data and make it ready for your machine learning model. There is SciPy, which is good for scientific computing. SQL Alchemy, it's a really good library for querying SQL databases. For example, your data is sitting in a SQL database, you might use this library to actually send SQL queries to the database to get the data and put it in the data frame. But at the end of the day, you always go back to pandas and use it for manipulation. You have NLTK, for example, you are dealing with the text data, and NLTK is a very good library to help you with that. You can do lots of things with that. Remove stop words, limitize, like all these concepts of natural language processing. If you're scraping data, these are two libraries that are also really good. So Beautiful Soup and Scrapy. And maybe scraping means you're going to the web and trying to get data from an HTML page, or like you're going to Facebook trying to scrape data. So those are two libraries that you might want to use if you want. For machine learning, scikit-learn is the main library. So if you want to learn any basics of machine learning, scikit-learn is your library. TensorFlow, Keras, PyCaret to a lesser extent, and PyTorch, very powerful, developed by, I think, Microsoft, but I think it's less used than TensorFlow, which is supported by Google. Okay. All right, so do you guys have any other questions before we start the hands-on? I think we're going to take a break and then we can start hands-ons. We will start with Python and Python basics and build up from that. So, okay, so we have a few questions. Can you explain why prevalence of pneumonia is extreme in 2 hospitals with chest x-rays examinations? So that was just a use case to illustrate an example. I don't think that's a real use case. So probably that's not gonna happen in real life. So it was just a use case to illustrate the problem that you might happen where model can learn some bias or hospital bias. Okay, so if we don't have any more questions, we can take a break. Let's come back at 12:30 and we can start the hands-ons. Okay. All right. Okay, I think we have. Okay, we'll wait a couple of other minutes. Nana, is everyone set up with Codio? Stacy?
Anas, yes.
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 Yes, everyone has Codio.
Okay. Okay, and so, okay, because I want us to actually do the hands-ons, and yeah, okay.
Yes, everyone has Codio, and they did it the first module, so they should be fine now. Yeah, if
Right,
anyone
good.
has issue, let me know in Slack, and I'll send you the link for you to sign up.
All right, good.
All right.
Okay. All right, so I'll share my screen. Where is it? Okay, so I'm assuming everyone has access to this, and you will find the slides under this module here, and then the notebooks that we're going to use are going to be under this this module here. And if you access it, you want to land here, and you can see the 4 or 5 notebooks that we're going to try and go over. So what I will do, I will be looking at the chat and seeing whether you guys have access. So just say yes if you are here and able to actually see the notebooks. Oh, okay.
Hello, do you have a
Yeah.
token?
All right, so you guys can hear me. Okay. All right, I'll
Yeah.
share my screen. I see that a lot of people are actually have access to the notebooks. So, all right. So what we're going to do, and I understand that some of you are advanced, some of you are novices. So we are going to do some Python refresher, and so I'll go through this and quickly and just demo some of the basics of Python. And these are notebooks for you as a reference, so you can go back and run them at your own time. And the way I wrote these, it's kind of like a tutorial, so you can follow along and try to understand the concepts. We'll do some. I'd like for everyone to try on and like get their hands dirty. So on the Pandas visualization, I want you guys to actually do some coding. And then the data visualization also, we might do some coding. And hopefully we can go through these 3 over here. And then tomorrow we can do the exploratory data analysis. So we'll take the diabetes data set and try to do the exploration. And then we're going to look at a completely different type of data, which is time series data of COVID, and try to plot those growth figures that you've seen everywhere during the past year. Okay, so the main important thing, this is a notebook. I'm assuming you guys got familiar with this during your last module. The idea is that you can quickly see here, for example, your Python version. You might also want to check the kernel that you're running, because mostly now we're using Python 3 and no one anymore uses Python 2. So that's also an important thing to know if you're just starting to learn Python. We can often run this command to see what Python version we have. And it is often also that there might be 2 versions of Python installed or in your VM. And that's the case here. So if I do Python, you'll see that it's 2.7. If I do Python 3, then it shows that it's 3.6.9. This is the quick sort function. And if you've coded in C or C++ or Java, you'd know that this would take you almost a page of code to actually do. So in Python, it's almost like a pseudocode, and also you have these things called expressions here that can allow you to quickly access lists and manipulate lists, and that's why it's great with the data manipulation analysis. So one other thing about Python, it's dynamically typed. So when I say x equal 10, I don't need to say integer or int x equal 10. It's usually just say what it is. If I do this, like for example, assign, like let's call it name to this, then it will be a string, right? So it's dynamically typed. You can also, these are the few functions you can do. So plus, minus, multiplication, and exponentiation. What else? You have these like shorthand notations that can allow you to, for example, do x equal x plus 1. So, okay, so someone said zoom a bit. What I will do, I'll actually do this. Is this better?
It's still small. So you use the plus sign on the left to zoom it. Yeah, that one worked.
I mean,
yes.
All right. I think
Yes.
this is good, right? Okay. All right. So we can use these. So basically, what this is, it's just x plus 1, right? Oh, we need to make sure it's actually the integer. You can run this. You can do this, and if I go back to what I did, it's the same thing, right? So I'll still get 11. Wait. Oh, because I changed the value, multiplied it by 2. But here, up. Go back here, I get 11 and 22. So it's just like small notations or shorthand notations that can help you write less code. We have this function called type that can allow you to see what the type of a variable is, and you can also use the print function and just comma to view a lot of other variables. So when you multiply, for example, you add an integer to a float, you still have a float at the end. So if we run this, you can see here that we started with the float, and then the type, we printed that, so that's the type, and then we have made some operations on the float, and if I multiply 2 times 2.5, it's 5, and I still have a float. Huh. Nana, does anyone else have like
No.
writing rights on this?
No, that's just you.
That's
Did it
strange.
reload?
Okay, going back. All right. Okay, so we can also use booleans, so true, false, and so those are common. It's common data type, so you can use it for events, like did the event happen or not. We have these operations, logical operations, so you can use and, or, not, or different. So T different from F, and it can tell you whether it's true or false. Strings are also important to learn how to manipulate. I'm not going to go through this, but you can just on your own come here and kind of like get familiar with all the types of string operations that you can apply. The important part of this refresher is the containers. So where does your data exist? And there are few types of containers in Python. So we're talking about lists, which is basically an array. And the power of the list, it allows you to access the list by index. So we can access, for example, the index. Here we're printing XS. Let's do this. Like, for example, I can print the whole list by doing this. Or I can print the first, the actual, the index starts from 0. So you can actually print the 3 or the 1. And you can also do this. And it's actually goes from the back, right? Like, so your instead of like going, the index goes from a positive number 0 to 1 to 3, 0 to 1 to 2, you actually go from -1. So -2 would be 1, right? All right. One other thing, strings can be also used as a list. So you can actually access each string or each actual character by providing the position of the index. You can append, so you can add one value to your list, and it can be mixed. So you can have integers mixed with strings, and you can use the append function to add values to that. Okay. I think we have a question. I'm trying to access the chat, but I can't see it. Some reason I can't see the chat. Okay.
It's saying, can you go over the quick sort code?
So I would. We have a lot of code to go over that's actually relevant to data exploration, and this is like I recommend like you go through it like yourself, but it just creates a pivot, and you are creating the lists on the left, right, the right of the pivot, and you're again applying the quick sort on those lists. So it's kind of like you find the middle and you pivot, and then you apply the function on the left side, apply the function of the right side. So then you're actually organizing your lists and ordering your lists using the pivot. So it's very useful to actually print the values. So once you go over this on your own, print what's the pivot when you feed it this list, and see what are the steps so you can debug it. All right, so we can do slicing with Python. So you can get a list, and then you want to only see the values from index 2 to 4, then you can do that, and you see the values from 2 to 4, which is 2, 3, and 4. Loops are also very important in any data science project to understand. So you can, and it's very easy way of doing that in Python. So you can identify lists, and you just identify any variable. You say for x, for x, for example, doesn't have to be, and then you can plot you can actually loop through your variable and print it, okay? Or to loop through the list and print it. We can format the string, so we can actually add the index. So when you use enumerate, it's also a very, very good function to know. When you enumerate through a list, it gives you back 2 values. So it gives you an index and the value of that list, okay? And you can print here the index of the value and the animal that we're interested in the list. Okay, so list comprehensions are very good if you want to write less code. So instead of, for example, saying create a square, for example, applying this square here. So what we're doing here, we have a list, and we want to square each value, right? So what you'll do, you'll go through the list. So you, for x in this list, append, and we're appending the square of 0, then the square of 1, then the square of 2, the square of 3, the square of 4. So this is one way of doing this. You can also do this short expression or list expression. So what I'm saying is x exponentiation to 2, so x squared for x in numbers. So it's taking x from numbers and getting the square for each variable. It's just another way of writing the loop. And you can also add a condition here. So if we just want the mode of 2 or variables that are divisible by 2, then the output of this would be 0, 4, and 16, right? Because you're only able to give the variables that actually satisfy this function are 0, 2, and 4. So 0, 4, 2 square, and 4 square. Okay, so moving on, dictionaries. Dictionaries are very important because you might end up, it's always that you might end up with an index with a value and whether that value exists or not, and you can use dictionaries for that. Also, you can use dictionaries for mapping. For example, I have multiple races and they're all mapped to a certain variable, like 1, 2, 3, 4, 5. So having a dictionary that tells me, okay, these are the race values, and you can use that as a dictionary and use it in your data manipulation. You can access dictionary keys using the key. So here we have cat, and this is the key here, if you see, and the cat is cute, dog, and this is the key and value. So it's a key value map, And to access the value queued, you want to do the dictionary, and then you like specify what's your index, okay? What's your key? Now, for example, if I don't have a value, I just have if I don't have a key in my dictionary that corresponds to monkey, it wouldn't work. It would just return error. You can also use the get function to get values. Like you specify key and you want the value, right? So if we run this, this says if you don't find monkey, a value for monkey, then return NA, which is kind of like a placeholder saying it's empty. And if you find fish, then just return the value of fish, which is I'm giving it a key here, and it's returning the key for fish, which is wet. Okay, so to iterate through dictionaries, you want to use items. So you say d.items, and then you'll have the actual key and the value. So here, this is key. Let's rewrite it. Value. So it's a key value pair, and key value. And then we can use the format to actually format these this string. So we say a person has 2 legs. So it's taking the key, putting it here, taking the value, putting it here. Okay. Okay, we'll keep going. So we also have sets. I'm not going to go through all of these. There's also tuples. And these are all useful to actually learn. So spend some time, try to understand the code and run it, or explore more about these types of data sets or containers, because that's where your data will sit eventually. Functions in Python usually use a keyword def. You define your function, a name for your function, and then what are the parameters that you're passing to your function. And then you have a colon here. There's always this indentation, so that's important, and it's often like automated, just like hit enter, you see the indentation. And we're creating here a function that just gives us the sign of x, okay? So if x is, okay, so for x in this list, can you provide me with the sign of x? And so we created a function that can provide us with the sign of each value in a list, okay? And we can also use, this is also important, is optional keyword arguments. So if I provided a value, I don't have to use the that specific parameter in my functions, okay? So I can do hello Bob, and that would print hello Bob. But if I say loud equal true, then it just uppercase it, right? So it's a concept of like not all your arguments or not all your parameters are always going to be there, and you might create some use case where you just say, okay, this is the default value for my parameter. Okay. All right. So I think I kind of like went a little bit quick through this, but the idea is it's there for you guys. Go back, try to run it, try to understand the concepts of, especially of the containers and how your data, you can manipulate your data. All right, so next I want us to get our hands dirty, and also I want you to run the code with me. So it would be good if you have a setup of 2 screens, or like you split your screen. But this is the Pandas Basics, and we're going to go through this and try to manipulate some data and kind of like put it in a format that we can maybe analyze later. Okay, so this. Okay, so everyone has this open? Okay, yes, yes, yes. Okay. So someone said my code view is different. It's just, I'm actually just using the file open because I want to actually make it bigger. But you can actually work here in the same container inside CodeView. Okay. All right. So Pandas is the key for data manipulation. And the name Pandas came from panel data, which is an econometric term for data sets that are that include multiple observations throughout a time period. What you can do with Pandas is upload your data. So you can upload it from JSON file, from CSV file, from Excel file. You can create some basic reports like statistics. So you describe your data, and that's very easy with Pandas. You can also do some visualization. So those are like few things that we can do, and we're gonna explore next. Okay, so the first step is to install it. So you can either use run here, or you can hit Shift Enter, and that would run this.
And as can you
Yeah.
please make the click on the not trusted up there, not trusted, and make it trust. Yeah, exactly.
All right. Ah, that's reloaded everything. Okay. All right, good. Okay, so I'm hoping everyone installed this. So what this does, it's telling when you use this exclamation point, you're actually running a command line. You're not running inside your notebook. Like for example, you're not writing or running a Python code. You're not saying print print 5. This is running within your notebook. This is a Python code, right? But if I do this, I'm actually installing this. I'm running it on the command line or the terminal of the VM. Okay, to import your pandas, you use this import pandas, and you use this shorthand, and this is very common and very known. So we usually say as PD, or import NumPy as NP. We specify some options for displaying the data. Usually the display, I think, is 5 rows for pandas, but this allows you to, when you view the data, you display 10 rows. So you just run these two, and we'll start exploring. Okay. So one way of, just as an example, this is a dummy data set that we can create, and it's using data dictionaries. So this is a key, and the key has a list, right? And this is another key, and the value is a list, and age, and then you have certain numerical values. And you often won't have to do this. This is mainly just for testing. So what I'm doing here, I'm creating a data set that we can actually use for manipulation. So to create the data frame, I would do df and use the data frame function and then data. Okay. actually it's the data frame. And you can run that. And, oh, we have to run this first, then you run that. And then you can view your data frame by just typing df and then viewing your data frame. Okay. All right. Okay. So, since I'm not seeing anything in the chat, I will keep going. Do you guys need more time to type this? Okay, moving on. All right. So it is often that you want to index your data. Okay. And when I'm creating the data set here, the index was automatically assigned. So I can, if I want, I can just do df.index and view my data set. And it tells me the range. It starts from 0 to 4, and the step is 1. But sometimes I can write assign an index when I'm creating my data set. Okay. And that assigns an index for you. Then you can access your data set using the index. So I can do df.locate and then use one of these indices. Okay. Then you do this.
I'm sorry, I have a name error.
You're getting error?
It says name error. Apparently, I must have made a mistake when I put the in DS.
Yeah, you have to make sure that everything is assigned. The name error, I mean, like name error is like if I make a mistake, a typo like this. See, if you make a typo in your data frame, you might end up with a name error. So you need to make sure that all your variables are named correctly, and when you refer to them, you actually don't make a mistake.
Okay. Can I get the name again for the data frame? It's df equals pd.
df equals pd.data frame. And you can copy paste this index.
One thing we want to add is that the data frame, the D and the F, we have a camel case here, and that's also you have to take care of that. It has to be uppercase D, uppercase F, because case sensitive.
Yeah, everything is case sensitive. Yeah, as William said. So if you I mean, if you write it as is, did you run this data? So it would tell you, for example, if I say data S with an S here, it will tell you what name is incorrect here. So just make sure that your variable is, you refer to your variable with the right name, and it's case sensitive, like William said. All right, I'll paste my code in the chat. Here we go. All right, this is not very important. You can, I will share the actual code so you can actually run it. I want us to get to some of the actual patient data. So you can use Pandas to read data from almost everywhere. So I have some data sitting in a GitHub repository, and it's synthetic data that I generated using this library here called Cynthia. So this is a great spot if you want synthetic data to do any research. They also have some COVID-19 data sets. So this is a great, and childhood obesity. So it's a great way to actually analyze some synthetic data and do some visualization or practice. So I have the data set in there, and what I will do, we want to create a patient's DF, and then you do PD that reads CSV. So I'm reading a CSV file, okay? And I have a CSV file here sitting in the GitHub. So read CSV, and it's called patient CSV. Now, how do I get to this path? Usually you would need to provide Cynthia. You would say Cynthia data plus and the name of the data frame or the name of the file I'm trying to read. Okay, we need to run this, and then we can use the data frame. So we use the function called head. And then this would show you the data I just read from my repository, okay? Anyone was successful in doing this? So we only have 20 minutes left, and I really want to go through this. So I might actually try to go through this faster, and I will share the complete code. So we can tomorrow and I really recommend you go through this and you try to understand what we do here. So now that you have a data frame, you can actually access all the columns by doing dot columns, okay? And I can see here that I have an ID, a birth date, death date, an SSN, drivers. So it's easier to see the columns this way than actually scrolling through this, because you might have hundreds of columns, okay? Okay, so we might also be interested in subsetting our data set, right? So what if I say I'm interested only in the ID, the birth date, and up to here? Just few columns, that's all I need. Columns of interest, right? So I can add, for example, gender. Let's do this, add gender here. And then what I'll do patient DF and specify the columns. So I'm saying I'm accessing this data frame or this table. I'm saying, hey, give me only these columns, right? Now, if you want to actually, so this doesn't save your data frame, right? It doesn't really save your data frame. So what you want to do is do this sample patient. So I'm assigning it to a new data frame, okay? Now I can actually view it again. So the variable is saved in the memory, and then I can export it. And one great thing about Pandas, you can export to multiple types of files. You can export it to Excel, you can export it to CSV, and you can, let's do this. So what I'm doing here, I'm giving it a path, and this path will be going here, will be under exports, okay? So if I run this, let's call it 1, then I go back here, you'll see that it was exported, okay? You can export to Excel as well. So there's an Excel function for this. So for Excel, you have to actually install another package called OpenExcel, which OpenPyExcel. But it's just good to know that you are able to export to different types. So we're gonna skip that. Okay, so again, so back to our patient's data frame, DF, we can do head, and I can actually specify the number of rows I want to show. Okay, can do 15. I see 15. I can do 2. So it's just the number of rows I want to explore. You can also do tail. So you can do tail, and what tail does, it just shows you the last rows, so the last 5 rows, and you can see here it's the last index, so we're seeing the last 5 rows of the data frame. Okay, I'll give you a minute to kind of like run this, try this head, tail.
We have a question in there. It
Yeah.
says, can you go back to the code for subset?
Sure thing. Yeah. Okay.
Yes, please, because I missed it before. Thank you very much.
Okay, so I see that's why I added this. Okay, so I'll explain this. We'll add one. So what I'm doing here, I'm concatenating. So usually in Python, you can use the plus sign to put 2 strings next to each other. So it's just I'm constructing a path because I have multiple files here in that directory. So I just want to construct, like, have a path and then add just the name of the file I'm interested in. Okay, so what this does, it's just like puts, you see here, it adds to the end of the string, it adds the name I was interested in. Like you can do this, my file, and then you can do test space. And if I run this, it would just give you the 2 strings concatenated. Okay.
Instead of typing the whole thing again, right? Instead of typing the whole string again, that's what you did.
Instead of typing it, and usually if you have a long string like this, you just put it in a variable, and then you just use the variable and you just add to it. Okay.
If anyone is having issues with the code, just do a screenshot and paste it in Slack, and the TAs will help you figure out what you're doing wrong.
Yeah, yeah. And also, like, the solved version of this, all the code runs. So I'll make sure that everything runs correctly, and you can just go and practice and run the nodes. Okay, so one other function that's actually really good to know is info. And this gives you an idea of all your columns and whether you have some missing data. So you can see here that we have some missing data in the driver's license, some missing data in debts, which is this one, for example, for debts, it's not really missing data, but it's more the person is not dead, right? And just gives you like a high level description of your data frame. We can also do this. So patient df.shape, which is an attribute of your data frame, and it tells you the number of rows and the number of columns. Okay. Okay. And then if you do D types, it gives you the types of the columns. So this is kind of like I already have the types of columns if I want, but if I want to access just the type of columns I'm interested in, I can do this. Okay, one other thing that you can do, or like one other function you can use is null, and we can do is null. And this also tells you, and what this does, it gives you an indexing. So it's a Boolean indexing. So whether the value is missing or not. And you can see here for death date, the value here is missing, right? So it's just like an indexing, and it's telling us false, true, where there is an empty value. And what you can do with this, we can copy it, go here. I can do sum, and then see what are how many missing values I have for each variable. Okay. You might want to do print if you want to see everything, I think. No. Some values. Nope. Yeah, you might want to actually export it, or there are other ways of actually seeing the full list of the sum. Okay. What we can do is drop NA if we want to get rid of, and this is very important because we're gonna build up on imputation. But when you have missing data, you need to make a decision on what to do with that missing data, right? Either like you omit it, you just delete it, and you have to be very careful with that because, for example, the information that is missing, it's missing for a reason. So you can't just like delete the data. So it is a decision to be made based on the use case, okay? This function does, it drops NAs. So let's see. So shape. So this really tells us that only 2 rows in the whole data frame are complete. So once we drop NA, we drop in all the rows that contain at least one missing value. So that's a use case where you want not to do that, right? You want to keep your data and make decisions about your data missingness. One other thing, if we want to drop columns, we can do this. Drop a column if it's all missing. So you could use access equal 1. So this refers to columns instead of rows. So think what happens here. Let's see how many columns stay. We had 25, right? So if I do this, then only 17 columns are left. Okay. And the way you check the shape, I was doing this here, but you just use this chained functions in Python. So you have a series or like an output of data, and you apply another function next to it. So this goes here, and then we can view the shape here. Okay. Okay, so any questions so far? I don't think we have a lot of time left, so I was like actually hoping to go through 2 of these. Okay. I'll try to go through at least few steps. So, for example, if I want to look at the zip function, a zip column, and see how many are missing. So I do this, right? Is null, and that returns that indexing, right? But what I want is actually the number. So I do shape or sum, actually sum. So I'm summing, and that gives me 543. How many patients, how many null values are in the zip column? And of course, you can apply this to any type of columns, right? What we can do with this, a simple imputation would be just replacing it with unknown, right? Although there are like more advanced ways of imputing. Okay, fill, you would use the function fill NA. I can't type. And then you would specify what value you want to fill the empty values or the missing values. And you can see here, there is a missing value and we just gave it unknown. So also note that we're not changing the original data frame, because if I do this again, if I plot this or like see it, the value is still there. So often what you want to do is to assign it back. So I say fill NA, but assign it back to my column. Now if I look, it's saved, and I can actually look at is null, that's sum, and see that actually there are 0 missing values, okay? Okay, so I'll try to go through this a little bit fast and at least to cover this. So what I'm doing here, I'm reading another file from that GitHub repository, and it's a table called encounters in a CSV format. So when we look at this, it shows us that there's an ID of the patient, there's a start and stop of that encounter, of the patient encounter. So what I want to do is to create a column called duration of stay or duration of encounter, right? So that could be useful for many types of analysis. So what I need to do, okay, so we're viewing the data frame here. Let's encounters dot columns. Look at df dot columns. Missing. Oh, I was typo. Okay, that shows me the columns, and the ones we're interested in is start and stop. It's 2 dates. We can do dtypes to view the values, and you can see here that they're objects. So I can't really apply a subtraction between 2 dates on object variable. So I need to cast them or change the type of the Python variable. So what we do, we convert the start and stop to date time. So pandas to date time, and then I give it the column, and I put it back in the column. So I'm saying this is a column in my data frame, turn it into a date time, and save it back to the start column. And same thing for the stop. Okay. Now we can look back at the counter DFD types and see if actually we changed it, and we did, right? So we can compute the difference between start and stop by first referencing a column and then minus the start, so the start column. So what it's doing, it has two series or two columns, and it's doing stop minus start. So I took some time. Okay. Okay, so it's taking some time to run, but this would be the last one we're gonna do. The rest I will upload a complete data set. And if you walk through this, it's just a series of examples and how you can filter your data, how you can subset it based on conditions, how you can use group by. So if I'm trying to understand, for example, what was the total claim cost, and grouping by duration of stay, I can do that. And then there are other functions here like mean, count, min, sum, and the group by function, which is very important. And like I go through it here. So these are all here for you as a reference. And please do go through them, because these are the core of data manipulation in any actually data science project. Okay, if I go back just to see if this ran. Okay, perfect. It did run. All right, so it would be a good note to end this. We added the column of interest, which is the duration of stay. So think about this as something that maybe you're going to build a regression, you're trying to predict your duration of stay, right? So you want to actually calculate that outcome or that variable and add it to your data frame. Okay, so that was it. I guess we didn't get to go to the data visualization yet, but we're gonna try to do that tomorrow and try to do one use case of data analysis.
Anas?
Yeah, so again, I know some of you have time conflicts, you may want to leave, but TA sessions are available. So if you need a TA session, you can make a request through Slack, and then one of the TAs will be able to assist you with that. Now, Adas, if you want to stay another 5 minutes or whatever, that's up to you to answer any questions.
Yeah, absolutely. Yeah.
Up to you. But otherwise, this has been another great session. And thank you, Anas, and thank you all for coming. And we'll see you again tomorrow at the same time, 11 a.m. Eastern Standard Time. So thank you for coming.
Mm-hmm. I'll stay for 5 minutes. So if anyone has a question.
Go ahead, Stephanie.
Are you sure? Oh, okay. Yeah, just one question about that output data table. It looks like your dependent variable is indicated in lowercase. All your independent variables are in uppercase, or do we determine that? Is that
you determine that?
Oh, okay.
You determine that there is no structure for that, and
so we can't
really that. Yeah.
No, go ahead. Go ahead.
No, what I meant is that was just an artifact of like coding, but like you can use whatever you want.
Okay, so we can't necessarily read somebody else's data table and infer automatically what their dependent and independent variables are.
Honestly, not that I know of. It
Okay.
might be, I'm not sure if there is some kind of convention, but yeah, I'm not sure. Yeah.
Thank you.
Anna, so I had a question. Well, first of all,
Yeah.
I thought that the training was very good information. Are we able
Can you
to
repeat that?
add,
I couldn't hear you.
I said what we did today was very good, very informative. Can
Thank
you hear
you.
me okay? Yeah.
Yeah, yeah.
I have a question, however, to go back over the exercises, will we have access to that, what we did today?
Yeah, so what I tried to do today, I left some empty cells in the notebooks so we can all practice, but I guess we kind of run out of time. So what we have or what we will upload, I think in both GitHub and in Codio is the complete notebook. So Nana, I'm not sure, do we have to actually publish it again or just like upload it to GitHub and people download it to Codio?
Yes, both ways. So you could do the changes, then publish it, and they will get it.
I just don't want to overwrite people's code.
Yes. So I did a small video on how to rename a file in Codio. I'll paste again in Slack so you can look at it. So what you could do is rename the file, Anas, and then publish it.
All right,
So
I will rename all those files and do _solved, and that way you know that's the one with all the code.
Yes.
Great. All right. Thank you.
All right. Yeah. All right. Do we have any other questions or we'll adjourn until tomorrow? All right. Thank you, everyone, and I appreciate the questions. And please, you have the code. You just make sure you run some of it at least. And if you have any questions, we can pick up.
Okay.
Thank you. Thank you, Anas.
Thank you. Take care, everyone.
Thank you.